So I'm going to go through a fundamental idea here. I'm going to kind of fill in some of the information on this slide. This whole video is about area ratios, but first we're going to look at area ratios in similar figures. So this only will apply to two figures if they're similar. Let's say you had two similar triangles or something like that. So I wrote similar triangles, or you could just say in general similar figures. Like let's say you had, this will apply to triangles, circles, because all circles are the same shape, if you will, or hexagons, if they're similar hexagons, whatever, similar squares, whatever you want. This will apply to all similar figures, not just similar triangles. Okay, so here's the idea, and hopefully you saw this in class first, otherwise I'm going to kind of ruin it, but then I'll show you what's going on. Alright, so here's the rule, and the observation that we'll experience. If the ratio of corresponding sides of two similar triangles is, let's say, A to B, keep in mind we really just mean that's A to B, that ratio could be written as a fraction, comma, then the ratios of their areas, and this only happens in similar figures, you really want to underline that, then the ratio of their areas will be A squared to B squared. And we could also write that as A squared to B squared. Okay? So this rule happens in all similar figures. Again, if you're comparing two similar squares, two circles, two similar triangles, two similar hexagons, this rule will always happen, and we're going to start to observe it now. So in this example, we have one circle that has a radius that is 3 times the radius of another circle. How many times larger is the area of the larger circle as compared to the smaller circle? So there's a couple of ways to do this, all right? First, let us notice that all circles are similar because they're all the exact same shape. They're not necessarily the same size. So let's start like this. Let's actually first off, we're going to draw a picture and kind of experience it, and then we'll see how it fits into the formulas that we saw on the last page. So let's just draw some circles. Here's a circle with a radius of 2, and so I just made that up. And now let's have a circle whose radius is 3 times that size. So here's a circle with a radius of 6. Now let's look at the area of the larger circle as compared to the smaller circle. All right. So the area of the small circle is going to be pi r squared. The radius is 2. The area is going to be 4 pi square units. And the bigger circle, the area is going to be pi r squared. The radius is 6, so 6 squared is 36. Multiply it by pi. That's 36 pi square units. How many times larger is the area of the larger circle? Well, if you want, you could just kind of look at these and you could say, well, 4 pi, to get to 36 pi, what do? You multiply by 9. That means the area of the larger circle is 9 times the smaller circle. Another way you could do it is you could take the area of the larger circle, divide it by the area of the smaller circle. Pi divided by pi is 1. The square units cancel out. So 36 divided by 4 is 9. That means the area of the larger circle is 9 times bigger than the smaller circle. Similarly, so you might now we can kind of really apply the formula, concept, idea, whatever you want to call it, that I talked about in slide 1. And the way we can do that is we can say, well, even if you didn't draw the example that I have on the left, you could say, all right, well, these are similar figures. They're not triangles, they're similar. They're circles that are similar. We know the ratios of side lengths. We would call that A to B. That's going to be 3 to 1 in this situation because we know one radius is 3 times the radius of the other, so that would be a ratio of 3 to 1. And then we could say, oh, since we have similar figures here, the ratio of the areas is going to be A squared to B squared. We could square each of these guys, and that would be 9 to 1. So either way you do it, you're going to realize that the area of the larger circle is 9 times the area of the smaller circle. So you might just realize that you can use this formula, but you know what, you're not going to remember this forever anyways, so you should just have the courage and experience to make something up and, you know, make another radius that's 3 times as large, look at the areas, and see how they compare to each other. Either way is great. And again, notice that the ratios of the side lengths were in a 3-to-1 ratio, and the ratios of their areas was in a 3 squared to 1 squared, otherwise known as a 9-to-1 ratio. So the square of the side lengths, or the square of the radii, or the square of the apophthegms, which you haven't learned about yet, the square of those will be equal to the ratio of the areas of these similar figures. Again, they could be circles or pentagons or squares or triangles, just as long as they are similar. So circles, don't forget, are similar. So in this example, we again have similar pentagons, so we have similar figures, so I would underline that, that's important. We know the ratios of the areas is 81 to 225. So we know they're similar, and in this case, we know the areas. All right, so we know that the ratio of the side lengths, A to B, we know that if we were to square those, we would get the ratio of the areas, otherwise known as A squared. Compare that with B squared. So in this situation, they gave us the areas, so we would put 81 to 225 right here. That's the ratio of the areas. Now we might think, well, what is the ratio of the side lengths? Well, to work this way, if you have things that are squared and you want to kind of go backwards and figure out what those numbers were before they were squared, what we'll do is we'll actually square root each of these numbers. Square root of 81 over the square root of 225, that'll be 9/25. So the ratios of the areas of similar pentagons is 81 to 225. Since they are similar and they gave us the areas, we'll square root, and we have the ratio of the corresponding sides is 9 to 225. Hold on a moment. That should be 9 to 15. Be careful on that. 15 times 15 makes 225. And, you know, we'd probably like to reduce that. We could reduce that to 3/5. The ratio of the side lengths of the two similar pentagons, the side lengths will be in a 3-to-5 ratio. Just give us that reduced answer as your final answer. So excuse my math there. 15 squared is 225, so the square root of 225 is 15. Just be careful with that. Okay? So in this situation, we didn't even draw pictures. We just knew how similar figures' area, if we had similar figures, how their area would relate to their side lengths. So we again kind of applied this idea. Now remember, this only works to similar figures. So you got to be real careful there that you don't just assume that you can just do this with any old shape. So here, let's say the problem asked you for the ratio of the areas of triangle XWY, the ratio of that to triangle WYZ. That's what we're going to try and find. Now keep in mind, these two triangles, they are not the same shape. They are not similar. But area ratios, or ratios are just a comparison. They're just a fraction. They're just a ratio. So all we have to do here is find the area of each of them and make a fraction so that we can have the sort of comparison that they want. This is our goal. Remember, we want to try and find the ratio of the areas. Well, this is kind of weird because we don't actually know the base or the height of either of these triangles. So how the heck could we do that? Well, we certainly need a height. And if you drop that altitude, wow, that's not very good. That's the height. And notice that that's the height of triangle XWY. And that's also the height of triangle WYZ. So they have the same height. And oh, look at these tick marks. This base with one tick mark is the same as this base. They have the same length. So each of these triangles has the same base and the same height. Let's compare the area of triangle WXY, we'll make that ratio, to the area of triangle WYZ. Well, the area, and so I'm going to make a fraction bar here, and I'm just going to focus on each piece at once. The area of WXY, well, it's a triangle. It has a base, it has a height. Don't forget to take half. Okay. And the area of WYZ, that's this triangle. It has a base of B, and it has a height of H. Don't forget to take half. So right here, we can actually kind of clean this up. What is anything divided by itself? Well, it's 1. So a half divided by a half, that's really 1. B divided by B, that's really 1. And H divided by H, that's really 1 as well. What is 1 times 1 times 1? Well, that's equal to 1. So these two triangles are in a 1-to-1 ratio. Why? Because they have the same base and the same height, so they have the same area. So again, these were not similar figures. We didn't do any squaring or anything. We just kind of were careful and kind of figured this whole thing out. So this is kind of a cool problem. The challenge here is to find the ratio of the areas of parallelogram ABFE and parallelogram EFCD. So we're going to find the ratios of the areas. Now notice these two figures are not similar, but we can still do it. Again, you have to have the inspiration to drop down a height. Now notice, we're going to find the ratios of the areas of each of these. We'll find the area of ABFE, and we'll compare it to the area of EFCD. We want to look at that ratio. So I'm going to even write the ratio right now, and we'll just put each of the areas in their respective place. Okay, area of a parallelogram, it's just like a rectangle that was blown in the wind. It'll be base times height. So the area of the ABFE is going to be 5 times H. The area of this parallelogram, EFCD, well, the base is 3, and the height is also the same height as before, so we'll call that H. So the area is base times height, otherwise known as 3H. And H divided by H is 1, therefore the ratios of the areas is 5 to 3. So this problem was very similar to the last one, in that it felt like they didn't really give us enough numbers, but then when we dropped a height, in this case they gave us the base, in the last problem they didn't give us the base, we were able to figure out the ratios of the areas, namely because in both examples, both figures had the same height. Now that was kind of helpful for reducing and figuring out the ratios of the areas. Again, be careful, these figures were not similar. So we didn't do anything with squaring or anything like that, like the earlier examples with circles, let's say, or you could do it with squares or triangles just as long as they're similar.